Hello, my name is Nikola Stošić and I hold a chair in Positive Displacement Compressor Technology at City University Center for Compressor Technology. The center currently celebrates its 30th year anniversary. The lecture today is dedicated to one of the questions many students didn't dare to ask because they thought that it was too simple to develop a discussion on it. This is how to connect thermodynamics theory and compressor practice, how to explain a compressor process in the light of theoretical thermodynamics. Some of the students would properly notice that situation and inquire it. I would encourage them to question everything by stating that there were no bad questions, only the answers might be wrong. Therefore, don't miss or hesitate to ask questions. Books are written on that topic, and many of them try to explain that connection. Some of them clearly and successfully, unfortunately many of them by using too simple approach. Due to a sheer number of authors, it is not surprising that the explanations of some of them in some of the books contradict each other. Let us start from the very beginning by using a blank sheet of paper. Thermodynamics, together with fluid dynamics and strength of material, define compressor process and integrity of its components. All three may be agglomerated in continuum mechanics, but the traditional approach is to apply them individually. Thus, let us start with the elements of thermodynamics. Thermodynamics considers our world in two entities, the system and the surrounding of the system. The system is separated from its surrounding by the system boundary, which has area A. The surrounding is everything else except the system itself. The system contains a closed and constant mass m, which state is defined by the properties of the state. Temperature T, pressure P, specific volume V, which is the system volume V divided by the mass m, as well as any other combination of the state properties like, for example, specific internal energy, which is a product of the specific heat at constant volume and absolute temperature T, then specific enthalpy, specific entropy. You will immediately recognize that the specific volume is a reciprocal of density. Properties of state are extensive if they incorporate mass, or intensive or specific if they are defined within a unit of mass. Extensive properties, presented here in capital letters, are additive, or they may be added, while the intensive are not. Certainly, the surrounding environment has its own properties, which due to the large or even infinite surrounding mass stay constant during its heat and work exchange. Thermodynamic state is defined by three properties of state, or by two if the system equation of state is known, which relates the three properties between themselves. Thermodynamic process is a change of state which may be open when it starts and ends a different state, or closed if it ends at the same state. The properties of state are obviously properties which have the same value at the start and at the end of the closed thermodynamic process. Any exchange of work and heat will result in a change of the system properties. The first law of thermodynamics describes conservation of energy and states that a change of specific internal energy du equals the heat received delta Q and work delivered delta W. Since heat and work are not properties of state, a delta is introduced instead of a total derivative d to distinguish between the property of state U and small values of heat and work exchanged. This is defined for a mass unit in small letters and for a given mass in capital letters. Integration defines energy exchange during the process, which may be open or closed. If the process is closed, a change of the internal energy as a property of state will be zero. Therefore, the heat exchange will equal the work exchanged. To quantify thermodynamic work, it is good to consider that it represents a force F, which is a product of pressure and system area surface A, acting at its path differential ds. Since the area times displacement ds is differential of the volume, thermodynamic work is P dV. Once known, it is possible to introduce the work into the equation of energy as it is presented here. It is frequently overlooked that the only communication between the thermodynamic system and environment exists through the exchange of heat and work. In turn, both work and heat exist only while being exchanged. Therefore, work and heat are not properties of state. And where is our compressor within the thermodynamics? I'm afraid we need some adjustment to settle it properly, because the compressor exchange is not only the work and heat, but mass too, which change is not recognized within, and it is contradictory to the thermodynamic system which contains constant mass only. Therefore, we have to introduce the mass exchange by defining the inlet mass which goes into and outlet mass which goes out of the volume. Certainly, due to the mass exchange, the mass inside of the volume is not constant, but it is being changed. The volume V is now introduced under the horizon as a seminal system property, which moreover, due to the work exchange, is being changed during the process. One of the approaches which well connects compressor and thermodynamics is as follows. The first law of thermodynamics, the conservation of energy, tells that the system internal energy change du equals heat Q plus thermodynamic work W, which is minus PdV, exchanged through the system boundaries. By adding PV to both sides of the energy equation, it states that enthalpy, which is internal energy plus PV, change dH equals heat and VdP, exchanged through the system boundary. The mass exchange during the admission and discharge at constant pressure keeps temperature and the density constant too. In the light of the mass exchange, which happens through the inlet and outlet and takes enthalpy with it, the heat and work are now exchanged only through the volume boundaries, which are not inlet and outlet. Why did we need to employ this exercise with enthalpy instead of using equation of internal energy directly? Simply because the enthalpy is exchanged through the inlet and outlet carried by mass, by which the influence of the environment is taken into account. During the admission, the inlet mass carries internal energy, but it simultaneously works towards the compressor. During discharge, the mass taken out of the compressor carries its internal energy and simultaneously works against the environment by pushing mass out. If these two works are taken into account, the compressor work is a sum of the admission work, compression work, and discharge work. This sum of works is called compressor work WC, which compared with thermodynamics work W contains the admission and discharge work. This is presented in PV diagram, otherwise in engineering thermodynamics called work diagram. It shows compression work as area surface B12C and compressor work A12D, which consists of the admission work 0A1B, compression work B12C, and discharge work C2D0. A clockwise direction process is positive, while a counterclockwise is negative. It would be a good place here to finish our lecture today, but several added equations might complete a picture of the compressor process and settle it into the compressor practice, which defines it as a starting position. If the heat exchanged by the compressor is small or negligible, it may be omitted. Thus, the enthalpy change is now equal to VdP. The most common is to employ equation of ideal gas here, which somewhat limits generality of the further discussion, but offers a good connection between the position achieved by this lecture and common compressor expressions used in the everyday engineering practice. The equation of ideal gas states that PV, which is itself energy, equals mass times gas constant R times temperature T. The first derivative of this equation combined with the equation of the first law of thermodynamics in differential form results in well-known expressions of relation between pressure, volume, and temperature during the ideal adiabatic or isentropic process without heat exchange. These define the compressor work in function of the admission and discharge pressures and volume, which are widely used in engineering thermodynamics, which themselves are a good starting point for further studying of compressor processes. Thank you for listening. With that, we conclude today's short lecture. For any further discussion and questions, please get in touch. At the end, if you wish to get more information about compressors and their processes, please don't hesitate to visit our website, which link is presented here together with our email address.